Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Dave Ansell. Dr. Dave, what's new and great in the world of science then?
We saw quite an interesting story this week about some NASA scientists in Missouri who've levitated a mouse.
They've levitated a mouse?
Yes.
That's cosmic.
They're just using magnets.
No!
Because water, a mouse is mostly water.
Right.
And water is slightly repelled by magnets. So if you get a strong enough magnetic field, you could make a mouse levitate. You could also make you levitate or me levitate. But they were doing it with mice. So they got a 17 Tesla magnet. That's probably about 1.7 million times stronger than the Earth's magnetic field, or probably about 20 or 30 times stronger than the strongest magnets you'll find in the really, really strong, shiny ones. And they've levitated a mouse with it.
Well, I hope the mouse is looked after and wasn't harmed during such an experiment.
I think apparently it was a bit confused to start with, and then they kind of got used to it. The reason why they're doing it is because they want to study how things develop in microgravity, so sort of in space. If you're in orbit, there's very little gravity, and that can affect people's physiology, the way their bodies work. And the problem is sending mice up into space is really expensive, and it's a bit smelly for the astronauts up in the space station. So if you can do it on Earth, it's far, far cheaper. So they've built this rig so you can levitate mice. You can also study how water droplets behave with no gravity and how bubbles move through them and how heat moves through them. But I just thought it was quite cool, really.
Yes, it's just bizarre. What a strange thing. Maybe the mice would find humans smelly somewhere. Yeah, I'm sure animals do find things smelly as well.
Quite a lot of comments on the web also of people who desperately were really, really jealous of this mouse because they wanted to play.
I suppose so. Let's go to our first question. Dom has sent a question in to say, why is it that when you put a battery into a camera, the charge goes down really, really fast? Dave?
Slightly dependent on the camera, but yes, cameras are particularly known for doing bad things to batteries, particularly traditional alkaline batteries, the ones you buy in the shops rather than rechargeables. There's a couple of reasons for that. One is that particularly old digital cameras did just use an awful lot of power, so they would just run batteries down very quickly. The other one is that digital cameras tend to use an awful lot of power at once, so they'll use all the energy at once. So when you actually take a photo and it then does all the processing on the information, it's got flash, it's got an awful lot of computing on the information to store it on the memory card. That uses an awful lot of energy and it's in a very short period of time. So it needs to draw a lot of current very quickly. And alkaline batteries aren't very good at that. And they've probably still got sort of more than half of their charge left if you're using them in a torch. But they still can't produce enough current to produce enough power to run the digital camera, so they seem like they've gone flat very, very quickly. If you use rechargeables, although they can actually store less energy than an alkaline battery, they're much better at producing large powers, producing very high currents. So they can actually be more useful in a digital camera, and they'll last longer.
Hi to Dave, who sent an email in. So Dave's tonight, who says, what is the difference between sea salt and rock salt, Dave?
The clue is really in the name. Basically, sea salt you make by taking seawater and evaporating off the water and keeping evaporating off the water. Traditionally, they do these in big flat ponds called salt pans, until eventually all you're left with is the salts after all the water's evaporated. And that's what sea salt is. They still do this all over the world now. There's lots of places where it was done. There's a place near where I grew up called Salcombe in Devon, which was a place where they had some salt pans, and then they make salt from it. There's all sorts of names which to do with that around the country.
Saltburn, yeah.
Rock salt comes out of the ground. It's a rock. It's essentially the same things happened to it, but millions and millions of years ago. So you have some sea, like the Dead Sea, or a sea which is dried up. You've got lots and lots of water evaporating, and all the salt gets deposited. You get huge deposits of salt. There's immense ones under the North Sea. There's quite big ones in Cheshire and lots of big ones in Austria. And you just go down there with a pick and shovel and dig out the salt. And it's cool. And it's because it comes from the rock. It's called rock salt.
And it rocks. All right. Thank you very much for that one. Our next question from Time Traveller. Hello to you. Do big steel ships use electrical devices to reduce corrosion on their hulls, or do they only use anodes?
Small steel ships, if you put them in seawater, problem is they rust. Mm-hmm. And even if you paint them very well, you scrape them across something and then they start rusting away in this beautiful seawater. So what people do is they put on lumps of zinc. Now, zinc is more reactive than steel, and if you put two metals together, you actually create a battery. So the zinc will get corroded very quickly, but that will change the voltage of the steel, which actually stops it corroding. And so the zinc corrodes instead of the steel. These are called sacrificial anodes, and eventually they all dissolve away and you have to put a new one on. But it's a lot cheaper than having to rebuild your ship every couple of years. For very, very large built ships and oil rigs and things, that's too expensive. You need huge amounts of zinc and it all becomes impractical. So what they do is they essentially build the battery by using an electric generator. And they just make the voltage by using an electrical supply, and they have a cable which sticks into the water. They charge up the boat, and it doesn't rust. So yes, they do use electrical devices instead of sacrificial anodes on big boats.
Now, Francis in Peterborough would like to know, how do lie detector tests work? Do you know, Dave?
Okay, I think basically the idea is that if you're lying, you're going to be more stressed than if you're not lying. So basically they tend to look for signs of stress. So when people are stressed, they tend to sweat a bit more, their heart tends to beat a bit more. Because they're sweating more, their skin will conduct electricity better. So you have a whole series of different measurements which can measure stress quite well. And then you ask people questions, some of which you know they're telling the truth, some of which you know they're lying. And you hope that when they're lying, they're going to get more stressed. And therefore, you can tell that they're lying, which works fine on most people unless someone's very, very good at lying and they can cover up the stress. Or they can become stressed when they're not lying.
Gosh. The mind boggles, doesn't it? Right, OK, we've got Mike in Colchester, Dave, says, who's wondering if his sat-nav will run out of capacity or does it override previous destinations? Oh, good question, because I often think about that. You know, I mean, I haven't got one. I wouldn't have one because I like to use a map. I like, you know, there's nothing like having your map screwed up next to you, you know, or trying to
read the map whilst you're
driving.
Oh,
no, one wouldn't do that. No, I tend to sort of plot it out before I go and then think, where am I?
Having to stop, yeah, it's always good fun, that, yeah. I'm not quite sure what he means by run out of capacity. I guess it's remembering all the routes he's been to, all the places he's been to before. I would doubt it's designed. I'm fairly sure it would be designed to override previous destinations if you ever use up its memory, because I think if it did run out of space, it would probably cause all sorts of other problems and cause all sorts of things to crash in bad ways. So if the programmers have been good and have been thinking about it properly, they will have designed it to override old ones. I mean, saying that, I'm guessing for any route, it doesn't actually have to remember very much information. It only actually has to remember where you're going. It doesn't have to remember the whole route because it works out the whole route
as it goes along.
Yeah. Or when
and
you hit go there, it does a whole lot of calculations. It works out the best route to go. So it's not going to have to store very much information, and it has to store an immense amount of information to remember all the maps of the UK and all the possible roads and how they all link up. So it's probably you'd probably be very, very hard to use up all of its memory by putting in an immense number of destinations.
Well, all right. Well, also, Mike says, also stainless steel. Why is it stainless? I don't think it is stainless sometimes, because it's like you could put a finger on it, you know, that's it. Shiny saucepans and that kind of thing. So why is the stainless steel called stainless steel? That's what he's trying to say.
Okay, stainless steel, okay, you probably can stain it if you try really, really hard, but it doesn't go rusty, which is a really important thing. Normal steels, if you get them wet, and especially if you leave them in some kind of unpleasant environment with lots of salt and water around, they'll go rusty in no time. Stainless steels have got a lot of chromium in them. Up to sort of some of them up to 25%, about a quarter of them is chromium. Normal stainless steel is near sort of 13-14%. And chromium, when it's exposed to the air, it oxidizes and forms a layer of chromium oxide. In the same way as aluminium does. Aluminium is actually incredibly reactive, but when it's exposed to the air, forms a layer of aluminium oxide. And the chromium oxide and the aluminium oxide protect the metals underneath from oxygen and water and all the nasty chemicals. So as long as the surface of the steel can oxidise, then you get this layer of very, very unreactive stuff over the top, which just protects it so it doesn't stain or rust.
Now, one here from Joan in Braintree. She says, torches. When she was a kid, we used to have handheld torches, and when the battery was getting flat, we used to hold it in warm hands or near something warm, and it seemed to give them a slight recharge. Why is this? Good question.
It's a very good question. Again, that still works with modern batteries. Batteries are basically a chemical machine. They have a chemical reaction which pushes electrons from one side of the battery to the other side, makes the negative side more negative, the positive side more positive. The only way that they can get, and they keep building up and building up until the charge keeps building up until the reaction can't go on anymore. If you then complete the circuit through a light bulb or something, then the electrons can flow through the circuit to the other side and the reaction can carry on. Once you start using up most of the reactants, the reaction starts slowing down, which limits the amount of current you can draw. How fast is limited by how fast the reaction can go. It just can't move the electrons fast enough. Now, it's a chemical reaction, and if you make something cold, chemical reactions tend to go slower. If you heat them up, they tend to go faster. It's the reason why you can have a piece of wood sitting around in the air for years and years and years and nothing happens. But if you light it, if you heat it up to a high enough temperature, it will oxidise, it will burn very, very quickly. So when you heat up the battery, the reaction will go faster, so that last bit of charge can get used up very quickly, and you can produce enough current to light the light bulb for a bit. And eventually, you don't get any more current in total out of the battery, but you can get more useful current out. Similarly, if you make a battery very, very cold, it doesn't work as well. I was in Russia a few years ago.
Oh.
And I had
Yes.
I was visiting a friend out in Russia, and I had a digital camera with some batteries, and if it was about minus 10 or 12 outside, and if I'd left my camera out of my pocket for more than about 2 or 3 minutes, the batteries got so cold they'd go flat. Put them in my pocket and warm them up again, and they were fine. So, yeah. Similarly, if you warm them up, then you can get more current out of them. If you cool them down, you can get less.
I got this picture of you taking photographs in Russia, with, huddled in your coat, probably getting arrested or something. We've got Mucker on the phone. Hello, Mucker.
Hello, good evening, sir.
How are you, darling?
I'm very well, sweetheart. And you?
Yeah, fabulous. All right, darling, what's your question for Dr. Dave?
I'm asking Dr. Davis, regarding mobile phones, does it cause any problem regarding radiation? Because you have the phone at your ear, and is that a problem?
Okay, the kind of radiation that mobile phones produce it's called radiation because radiation is basically stuff which comes away from something in a straight line, sort of in a radius, like a radius of a circle.
Yes.
And so it's not the ionising radiation which radioactive substances give off, which is really nasty and can definitely give you cancer.
Right.
So it's a different kind of radiation. It's basically microwaves.
Yeah, okay.
So the same sort of things, very similar to the ones in your microwave oven.
Yeah.
And so it will have the biggest effect it's likely to have on your brain is it's going to warm it up a bit.
Okay.
But compared to a microwave oven, a mobile phone hasn't got very much power, and very little of that power is going to be dumped in your head. Some of it will be, but mostly it will just warm you up a little bit.
Okay.
There has been some research, and the only other possible way it might affect you slightly is that it's microwaves are a form of electromagnetic radiation, which means they can make electric currents flow in things.
Right.
So some people have suggested that because your nerve cells are electrical in nature, then it could affect the way affect currents. It could cause currents in your brain or something.
Right.
I have seen a while ago one piece of research which said that people actually thought better when they were using their when they had mobile phone radiation going into their brains. They were slightly more intelligent. But it was only one piece of... So that might indicate that it could do something to the electric currents in your brain.
Thank you ever so much for your question. Thank you.
Thank you very much, sir.
All right, take care, sweetie. Bye.
And you, sweetie. Bye.
Bye-bye. If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Adrian has sent an email in, Dr. Dave, to say, "Hi Sue, can you please ask the doctor to explain the properties of sea salt and rock salt? That is, which is the healthiest?" Do you know about that, Dave? You've got your chef hat on now. He's a pasty bloke. There we go.
Yeah,
you know?
pasties are good. I don't really know of much difference in healthiness. Some people, I think, possibly argue that, there's two things. One is that it depends on the rock salt. Possibly you've had some other minerals being moved through the rocks that will end up dissolved, mixed in with the rock salt, so possibly that's less healthy. But then again, sea salt, the sea's got all sorts of strange pesticides and things which humans have been putting into it, which will get concentrated when you evaporate off all the water as well. So I certainly don't know of any significant difference between the two.
All right, well, Mike is wondering about the human brain and his sat-nav. Does the human brain override or delete information, or is everything stored forever? That's a cosmic question, Mike.
A very good question. Again, not my areas of expertise. I think your brain... I think your brain tends to sort of override things, but in not the way you're thinking of, not the way a computer does overwrite information. Your brain sort of seems to keep memories in a very kind of distributed way. So as you sort of overwrite more and more memories over the top, they tend to get fuzzier rather than disappear entirely. And they also get harder to access. So as things get further and further in the past, if you have something to remind you about them, so you get a bit of the memory, then it's easier to get back the rest of it. But the access gets more and more difficult as you overwrite more of the memory. And also it becomes more fuzzy. You lose detail rather than the overall impression. So when you're 5, you might remember kind of your impressions of the house, and that the house, and it was big, and that possibly it was green, but you might not remember all the details of the furniture and things like that. So I think memories tend to, rather than getting overwritten, they tend to slowly get more and more fuzzy.
I think you need a trigger as well with things, don't you?
Yeah.
Like if you see a photograph of somebody that you knew or something, oh yeah, I remember that, and then gradually that kind of stuff comes back. Yeah, it's interesting stuff.
It certainly gets harder and harder to access.
It's all cosmic, that's what I say. Dr. Dave, says Sean in Hertfordshire, how do humans survive the power of a lightning strike?
Yeah, lightning strikes are quite scary things. They can have up to sort of 1 million amps for a very, very short period of time. And if they hit a tree, they can cause all sorts of damage. If they hit a person, you will get really, really bad burns. You have very, very large electric currents flowing through you. And that will heat you up, and it will cause burns, particularly where they enter and where they exit you. And you can have nasty burns in between the two. If the electric current flows through your heart, that's when the real problems come, because your heart's beating is controlled electrically. And so if you've got a big electric current going through your heart, then that can cause all sorts of havoc with the heartbeat. But if most of the current avoids the heart, if you get less than a few milliamps through the heart, then it's quite possible to survive it, which is why the instructions I've heard of surviving lightning storms, if you're in an open area, it's to sort of hold onto your feet, keep your feet together. Because if you have a lightning strike near you, if you keep your legs apart, then the current will be flowing through the ground.
Oh, right,
and so go up through one and back down through another one. And the other one is to lean over and put your bum in the air. Because if you're going to get hit by lightning, you don't want the current to go up through your head and then through your chest, through your heart. Because you want to keep the current away from important things like your brain and your heart. So if you stick your bum in the air, then the current's going to hit your bum and then flow down through your legs and into the ground. It will hurt a lot and it'll be very unpleasant, and you'll get nasty burns. But it's not going to stop your heart, or it's much less likely to stop your heart. So basically, it's going to do you a lot of damage, but as long as it doesn't hit your heart, it's not going to kill you.
Right, OK then, so that's a bit of safety there. So if in doubt, if you're sort of stuck somewhere out in the lightning, if it's suddenly, if you're out for a walk and suddenly thunder and lightning and that, don't go stand under a tree. Just
standing under a tree is a bad idea.
Stand with your feet. Be with your feet together and hang on to them.
I have heard that you should sort of hang on to them, but you don't want to make too good a contact. You'd rather the current flows down through you.
Right. OK.
The car is probably the safest place to be. It's not the rubber tyres. The rubber tyres won't help you at all because the lightning has travelled through air for hundreds of metres. 6 inches of rubber isn't going to help you. What it is the fact you're in a big metal box, which means that when the electric current when the lightning hits the car, electric current flows through the metal far better than it will ever flow through you. So the car might get a bit warm and all the current might flow through the car and it's probably going to blow out your tyres, but you'll be fine.
Right, that's that then. Now then, Tad says Jupiter is clearly visible in the night sky at present, but the lower it is on the horizon, the more distorted its image seems through a telescope. Is there any reason for that?
There's a couple of reasons. One of them, most of them to do with the fact you're looking through more atmosphere, and also when you're getting very low on the horizon, there's going to the light which goes through which comes to you from the bottom of Jupiter is going to have come through thicker atmosphere than the light which comes through to you from the top of Jupiter. Which means more atmosphere, which means it's going to have gone slightly slower, and that means that light tends to bend slightly, refract. In the same way as when you look through water, if you look through water in a curved jug or something, the image behind it gets all distorted. So the image you see of Jupiter will get a bit distorted because of that. The other thing is, as you look through more air which is low down, close to the ground, you'll see more air which is warm, more variations in temperature. You'll get little updrafts in some places. So you'll get more kind of shimmering effects, like if you look over a hot toaster or something, the image behind it all shimmers a bit. Because you're looking through lots of more warm, turbulent air, you'll get a lot more shimmer. And so it'll be harder and harder to see. And of course there'll be more dust and things, so there'll be more fuzz in front of it.
You started me feeling hungry now, thinking of taste.
The same way as the sun tends to look distorted just as it sets as well.
All right, Jim in Cromer says, I had gluten-free flour in a chocolate brownie and put it in the microwave to heat it up and only left it in there for a very small amount of time and it came out rock hard and the smoke that came out of the microwave. I know micro works fine, so is there anything in the flour that could cause this?
It's not something I've ever come across before. I mean, it's possible that it's just a very, very dry brownie and there's very little energy, there's very little to absorb to keep it cool. So normally if you heat up something in a microwave, then it'll get hot and then water will start evaporating so it won't get above 100 degrees C. I know fat absorbs microwaves very, very efficiently, so if there's some fat in the brownie, there's not a lot of water to evaporate to keep it cool. It could get very, very hot very, very quickly. I'd be surprised if it was anything specific about the gluten-free flour. I can't think of any reason why that would have that effect.
Might have been, oh gosh, and if I was there might have been...
Sounds like something which needs more experiment.
Yeah, sometimes if you put, something that's got flour in it into a hot place or an oven or a microwave, is to just sprinkle a little bit of water on top. That brings your crusty rolls up lovely. Now then, we've got Alan on the phone with a question. Hello, Alan.
Yes,
how are you?
There.
What's your question?
It's something that's quite current at the moment because we seem to be getting a bit of rain. I've noticed that on some days we get a completely blue sky and maybe the odd cloud, and from that cloud we'll get rain.
Yeah.
And then on other days the sky is absolutely grey, full of clouds, and it doesn't rain. What is it that makes the difference?
Okay.
Good question,
That's a very
Alan.
good
Thank
question.
you.
This is meteorology and is therefore very complicated because there's all sorts of different ways you can get rain. There's a couple of major ones. The first one you were talking about, where you get rain on we start off with a really clear sky. You tend to get a lot of sun beating down on the ground or on the sea. It heats up. You get some areas where that hot air rises, it expands, it gets less dense, and it floats upwards. Now, as it floats upwards, it cools down, and you get water condensing, and then you form raindrops. It all happens in a very kind of localised way. That's where the kind of fluffy cumulus clouds are to do with that.
Right.
And you can get rain under those. It tends to only happen in the summer because you need quite strong sun for it to do it. And in tropical areas, you get very similar kind of rain.
Yeah.
And it's very, very localised. You get very localised heavy showers. And so the rest of the sky can be entirely blue, but you get this local updraft of air. As it goes up, the pressure gets less, it expands, it cools, and you get rain there.
So it's fairly instant then. It goes up and then comes down almost immediately.
Or sort of within a few hours anyway.
Yeah.
I mean, in tropical regions, you often get 2 rain showers every day, sort of one at midday and one in the evening.
Roughly.
And so it happens. So the whole process will happen in 4 or 5 hours.
Right.
You can also form clouds where you get 2 different regions of air mixing or meeting. So if you get an area of warm, slightly damp air meeting cooler air, then that can cool down the warm, damp air, and then that can form clouds and eventually form rain.
Mm-hmm.
And that tends to be the kind of winter kind of rain we get. So you get the whole sky is grey, and you sometimes get rain coming from it. There's very different ways which it can happen in the winter, but especially if you've got warm air moving over cold air, then you'll get then it'll form. It tends to be a very spread out junction, and you'll get clouds which can go over hundreds of miles before it actually rains. Right. Particularly if the cold air isn't very cold and the warm air isn't very damp.
Does this depend on the height of the cloud as well? Because sometimes the cloud looks very low, and you think, "Oh, it's going to rain in a minute," and it never does.
It'll depend. It depends on almost everything you can think of, I think.
Oh, right.
I'm not an expert on meteorology, but certainly it'll depend on how the moisture in the 2 different air masses, the temperature of the 2 different air masses.
And sometimes they react against each other.
And it can sometimes you can even get rain which starts off very high, and by the time it should have hit the ground, it's evaporated.
So
is that drizzle?
Drizzle, it could form a drizzle. I think it tends to be more... Drizzle is basically when the rain is forming very low down. And so the droplets, water droplets in the clouds are kind of sticking together. They haven't stuck together enough to form big droplets. So they're forming very, very small droplets which fall down slowly. I expect there are other ways of making drizzle as well. So, yes, it's very complicated, but the summer ones are very immediate, and when you get a whole cloud cover, that tends to be air mixing. It's the whole warm and cold fronts which you see on weather forecasts are all related with this.
Right, thank you very much.
All right, thank you very much, Alan. Nice to speak to you again.
And you, Sue.
Thank
Bye.
you. Jill says, I'd like to ask the Doctor, Dave, about energy efficiency light bulbs. I don't think the media has given us the full news about them, and, for example, they have mercury in them, which I didn't know about until recently. What do you think about them, Dr. Dave?
There is certainly mercury in energy-efficient light bulbs and fluorescent strip lights. The way they work is by basically passing a spark through mercury gas, mercury vapour. That then gets lots of energy. It releases it as ultraviolet light, the stuff which makes your clothes glow in clubs and discos and things. And then they put the same stuff on the inside of the tubes, which makes your clothes glow, and so the tubes glow. There is mercury in there. There isn't very much mercury in each light bulb. I shouldn't worry too much if one breaks in your house, for example. It's basically a lesser of two evils thing. I think that the damage the mercury is likely to do, especially if you don't start going through the smashing light bulbs for the hell of it, huge numbers in one place, the damage the mercury is going to do is going to be far less than the energy which conventional light bulbs would have burnt. So yeah, it is a bit of a kind of scales thing, and mercury isn't very nice. Maybe we'll get LEDs fairly soon and it won't be an issue.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.